Hello, everyone. My name is Keegan Harris, and I'm a PhD student at Carnegie Mellon University. Today, I'll be talking about stateful strategic regression. Before I get started, I'd like to mention that this is joint work with my wonderful advisors at Carnegie Mellon, Hoda, Heidari, and Stephen Wu. Machine learning models and algorithms in general are increasingly used to assess individuals' qualifications for high-stakes opportunities. Some example domains in which ML models are used to make decisions about people include lending, education, and employment. So I'm sure, as you can imagine, several concerns arise when talking about using ML models to make decisions about humans. From the designer side, you want the model to be at least somewhat interpretable so you know why it's making the decisions it's making. It's also the obvious issue of fairness, in the sense that you don't want to deploy a model which will treat different subpopulations differently, possibly putting one at a disadvantage. These are both very important issues, and while a lot of great research has been done in these areas, they're still far from solved problems. However, the issues we chose to focus on in this paper are the downstream implications of machine learning models. In particular, there's this notion of Goodhart's law, which loosely states that once a proxy measure becomes a goal in itself, it is no longer a useful measure. For example, you could imagine a scenario in which a machine learning model is used by universities to predict the success of a student in college based on a set of features. And this score is used to help make admissions decisions. In a vacuum, the number of books in a student's home might be a fairly good predictor of college success, the idea being that students that read more are more studious. But the moment the model's use of this feature becomes public knowledge, applicants will just start buying as many books as possible and putting them in their home. So it ceases to be a good measure of college success. The area of research known as strategic classification or strategic regression aims to formalize this idea with the goal of designing machine learning models which are somehow robust to these strategic interactions. Strategic regression models the interaction between a decision making institute known as a principal and an individual decision subject known as an agent as a stackable game. Basically, for those of you who don't know, a stackable game is an asymmetric game between two players, a leader and a follower. The leader, as her name suggests, moves first, and the follower then best responds to the leader's action. The solution concept to a stackable game is known as a Stackelberg equilibrium, which is analogous to a Nash equilibrium in normal form games. In the strategic regression setting, the principal is the leader and the agent is the follower. The principal moves first by publicly announcing a decision rule. This can be a machine learning model, but it can also be something simpler, such as a grading rubric or a list of criterion that the agent will be evaluated on. The agent then best responds to this decision rule by strategically modifying their features. So, in the language of the example from the previous slide, by buying more books. Notice that in the strategic regression setting, the goal of the agent is pretty clear. They want to maximize their outcome regardless of whether or not they deserve a positive classification or not. Everyone wants to get into college, everyone wants to get the loan, get the job, etc. On the other hand, what the principal's goal should be is not as clear. The first thing that comes to mind is to minimize predictive risk by designing models which are robust to feature modification. And this was, in fact, the goal of many of the early works in the area of strategic learning. But is all feature manipulation bad? In a more recent work, Kleinberg and Raghavan distinguish between different types of feature manipulation. In particular, they make a distinction between what they call gaming and improvement. So, gaming is when agents take actions to improve their outcomes without actually improving the underlying quality the principal is trying to measure. An example of gaming would be cheating on an exam, since as a cheater, you're improving your test score without actually improving your knowledge level, which is what the test is actually attempting to measure. On the other hand, improvement is when an agent takes actions which improve both their observable features and the quality the decision rule is trying to measure. So, an example of improvement would be studying, which improves both your test score and your knowledge level. So, in this setting, the goal of the principal is to incentivize improvement, which basically translates to incentivizing the agent to invest in specific directions of effort. And this is great, but this, and to the best of our knowledge, all previous work in strategic learning is only capable of capturing sort of these one-shot interactions between the principal and an agent. In particular, many real-world settings are not captured well by this interaction model. And the question we aim to answer is the following. Can we develop models for strategic learning that capture this strategic interaction over time? And can the principal use these multiple rounds of interaction to incentivize further effort investments into desirable characteristics? So, sort of an example to illustrate this is the following. So, for example, consider a classroom setting in which a teacher gives a student an assessment. The goal of the teacher is to get the student to learn the material, while the goal of the student is to get a good grade on the assessment. So let's take a look first at this one-shot setting. Assume the teacher assigns a student a grade using a linear combination of two features, test score and homework score, denoted by the red circles in the diagram. The student has three ways to improve their observable features: by cheating on the test, by studying, and by cheating on the homework. And these are denoted by the yellow circles in the diagram. In this example, observable features are related to the score an agent receives through the theta parameters chosen by the principal, which is the assessment policy. Additionally, efforts translate into observable feature values through what we call effort conversion values, or the W's in the graph. Note that while cheating only improves one observable feature, studying improves both. If the W values are higher for studying than they are for cheating, then it is trivially easy for the principal to incentivize students to study. However, if it is significantly easier for students to cheat as opposed to study, there may actually be nothing the principal can do under this one-shot model to prevent them from doing so. Now let's see what happens when we take multiple time steps into consideration in this classroom setting. Having multiple time steps at the principal's disposal is a realistic assumption in this setting, since students are often evaluated multiple times throughout the course of a semester by their teacher. In this example, we assume that the effort spent studying accumulates over the time in the form of an eternal knowledge state, while cheating does not. This knowledge state affects both the student's test and homework scores. If the time horizon is long enough, the principal may now be able to incentivize a student to study in situations where it was not possible under the one-shot model due to the accumulation of knowledge over time through studying. The plot on the right illustrates this example. For a time horizon of 1, which is equivalent to the diagram on the previous slide, the principal cannot do anything to incentivize the agent to study. For a time horizon of 2, effort spent studying carries over from the first time step to the next, so the principal can now incentivize the agent to spend half of his effort studying. For a time horizon of 3, the student can be incentivized to spend 2/3 of his effort studying. And for a time horizon of 4, they can be incentivized to spend 3/4 of their effort studying. In general, as the time horizon increases, the principal becomes more and more successful at incentivizing the agent to study. So in this stateful setting, we still model the interaction between the principal and agent as a stack-or-bar game. The principal still moves first, but now they announce an assessment policy, a sequence of T assessment rules where T is a time horizon, which the agent will be evaluated on one after another after another. This can be thought of as the teacher announcing a sequence of evaluations at the start of the semester. The agent then best responds to the entire sequence of assessment rules by strategically modifying their features at every time step, and this is known as their effort policy. The goals of the principal and agent in this setting are analogous to their goals in the one-shot setting. While in the one-shot setting, the agent cares about maximizing the single score they receive, in the stateful setting, their goal is now to maximize their cumulative sum of scores across all rounds. Similarly, the goal of the principal is to maximize the cumulative effort an agent expends in a certain direction. So under this formalization, we are able to characterize the game's Stackelberg equilibrium by giving optimization problems to recover the principal's optimal linear assessment policy and the agent's optimal effort policy in response to this linear assessment policy. Next, we show that the assumption of a linear assessment policy is without loss of generality. In particular, we show that if an effort policy can be incentivized, then there exists a sequence of linear assessment rules which can do so. This simplicity is important because it means that the principal does not have to sacrifice optimality for the sake of model interpretability. Finally, while the space of optimal principal and agent policies is non-convex in general, we provide polynomial time algorithms to recover the optimal principal and agent policies in settings where the dynamics of the system can be reasonably thought of as being linear. So next I'll provide a quick proof sketch for the optimality of linear assessment policies. Analogous to previous work, we define the notion of a dominated effort policy, which is basically an effort policy which no rational agent would ever play. Similarly, we say that an effort policy is incentivizable if there exists a sequence of possibly nonlinear assessment rules which can incentivize a rational agent to play it. This leads us to our main theorem, which states that for any effort policy which is not dominated, there exists a linear effort policy which can incentivize it. The way we prove that is as follows. We are able to characterize this notion of effort policy domination by a linear program, and we show that if an effort policy is not dominated, then a subset of the dual variables of this linear program correspond to a linear assessment policy which can incentivize an agent to play it. The space of optimal principal assessment policies is non-convex in general, but if certain linearity assumptions are made about how agent actions translate to observable features, then tractable algorithms exist for recovering both the principal and agent's optimal policies. Given a sequence of assessment rules deployed by the principal, the agent's optimal effort policy can be found by solving a sequence of linear programs. The principal's optimal assessment policy takes the form of a bilevel multi-objective optimization problem, which are NP hard to solve in general. I'll now sketch the steps we take in order to recover the principal's optimal policy in polynomial time. Our goal is to use a membership oracle-based convex optimization procedure to recover the optimal assessment policy. In order to do this, we need three things. We need to be optimizing over a convex set, we need the function we're optimizing to be convex, and we need a membership oracle for the convex set. The set we're optimizing over is the set of incentivizable effort policies. In particular, we want to find the incentivizable effort policy which is most desirable to the principal. See the paper for proof that this set is convex. We're optimizing over a linear combination of components of this effort policy, so the function we are approximating is convex. Finally, we need a membership oracle for the set of incentivizable effort policies. Fortunately, our main theorem gives us such an oracle. Given an effort policy, we can determine if it is incentivizable or not by using the dominated effort policy linear program. Using this membership oracle-based method, we can now recover the effort policy which is most desirable to the principal in polynomial time. Once we've recovered the effort policy most desirable to the principal, we can use a subset of the dual variables of the dominated effort policy linear program to recover a linear assessment policy which can incentivize this effort policy. In addition to the results outlined previously, we explore the use of alternative models for the price an agent pays for modifying his or her features. Specifically, while we previously assumed the agent picks their actions according to some fixed effort budget, we compare with how the agent best responds when they are subject to a quadratic cost penalty for taking actions. Under this alternative agent formulation, we characterize the game's Stackelberg equilibrium and show that this modification can lead to significant changes in both the principal and agent's optimal policies. Also, while under previous models the principal may not be able to incentivize the agent to expend effort in desirable directions, we show that it is generally possible for the principal to do so under our model if the principal is able to pick the time horizon. We provide a bound on the minimum time horizon required to do so. So, in conclusion, we formalize the interaction between a principal and agent in the strategic regression setting, which plays out over multiple time steps. By considering multiple rounds of interaction, desirable effort profiles can be incentivized under a wider range of settings compared to models which only model strategic interactions in a one-shot manner. Under this setting, we characterize the game's Stackelberg equilibrium, and we provide tractable algorithms for computing both the principal and agent's optimal policies when the dynamics of the model are linear. We also show that linear assessment policies are optimal for incentivizing the agent to expend effort in certain desirable directions. There are several exciting directions for future work. Much work within the strategic regression literature assumes that all parameters of the system, such as how an agent maps actions to observable features, are known to the principal. It'll be interesting to relax these assumptions in our setting and design policies for the principal to learn the optimal sequence of assessment rules over time when these parameters are unknown. Extension of our model to a population of heterogeneous agents is also a natural direction for future work. So thanks for taking the time to watch our talk. If you have any questions or just want to talk more about the paper, feel free to reach out to me via email or social media. Have a good day.